Hello everyone. Today I am going to be discussing measures of variability. Oh, my graphics card decided it want to pop up. Measures of variability. It's called measures of variability or dispersion. So let's go ahead and dive right on in. So what this actually does is it describes the variety, diversity, or heterogeneity of a distribution of scores. So hetero means different. You can see that, homo means same. So again, variety, diversity, how different, and you get it, it's how things are spread apart. Another way to think about this is it is a measure of consistency, okay? Consistency being the key here. So variability refers to the degree to which a variable's values are dispersed, which is, how scattered things are. When you disperse something, you scatter things, okay? So, and the more scattered something is, the more variability it has. So they're useful for measuring consistency. I pointed that out in that bullet point there. And for example, while evaluating the ambulance response time of two different services, both average response times came out to be average of 7.4 minutes. Now let's compare service A and service B. And I'm going to break out my pen here. That's a laser pointer. Look at that. Anyway, so can I draw? No. Okay. So I'm going to draw up my pen here. See the pen? Now, if you remember correctly, this peak right here, it's called your kurtosis. Okay, this is important. Kurtosis. This is important. And this of course does have a kurtosis too. So that does have a kurtosis. Now, as you can see here, remember how I said both of these have an average of 7.4. Just to check that, just to make sure, 7.4. So these both have the same average, but they don't both look very, very, very much the same. Okay, they both look very different, I should say. Now, which one of these do you think has the highest amount of variability in it? In other words, which one has the most scattered dots in it? Now remember that this drawing line right here, it is an outline of the dots in the data. Okay, to kind of put this more into perspective, you see this number 150 here? If we hang it over like so, right here, we can say 150 times the ambulance response times was about 5 minutes. Okay? So, that's one of the ways to think about that. Now, which one has the most dispersion, or which one has the most variability? The answer is this one has the most variability, and this one is the most consistent. Okay, so you can see here the highest kurtosis generally means higher consistency. It just means that there's more data points. As I said, how this is an outline of the data. It means there's more data points at the top here. In this case, there is more than 300 data points that come down at 7 minutes. Whereas you go down to 7 minutes here, well, you got about 175. So, and the further talk about this point of consistency, you can see here, well, with a minute and a half response time, which is pretty darn fast, you got 50, but at the same time, you got 50 over here. This is a symmetrical distribution. So, 50 times they came at 13 minutes, whereas like this is like they came at 13 minutes maybe one or two times. They also came at 2 minutes, about 10 times I'd say. And so this is just very consistently has a response time between 5 and about 10 minutes, whereas like this chart is pretty much all over the place. So that is variability on a graph. And remember, this is the same ambulance. It's not the same. The ambulance service has the average 7.4. So just reporting the average isn't enough to get a big picture of what's going on with services when you're comparing services. And we're going to be comparing services in here because it's a social science to see, what works best. And since we're social science, we do a lot of service, so you'll be comparing services. So service A is less dispersion. As I said, it is more consistent with less dispersion. Service B is more dispersed. It's just farther apart. And the peak is called kurtosis. There's your peak. And service A has a higher level of kurtosis than service B. Now this is service A, and this is service B. Okay. So range is your high score minus your low score. Let's say, once I find my pen, let's say we got a distribution of 1, 3, 6, and 9. Well, the high score in this is 9, and the low score in this is 1. So 9 minus 1 is 8, and that's our range. And it's just a quick and easy way to gain a basic idea of variation in the distribution. I wouldn't use it. It's just me showing you like an example of how to do variation. What we're mostly going to be doing in here is called standard deviation. But we're also going to do interquartile range. So the interquartile range is more accurate, but it's also still very limited. So let's talk about interquartile range, okay? So we're going to do the same thing. 1, 3, 5, 7, and 9. Okay? So you can divide this set into quarters, 25%, 50%, 75%, and of course 100%. Now you do have a 0, but no one really seems to care about 0, so let's just ignore 0% exists. So now you have quarters. This is quarter 1. You can technically call this Q0. Q2, Q3, and quarter 4. Okay, just evenly divided quarters. Now the 50th percentile is what you call Q2 or median. Okay, it's called the median, and we do a lot of work with the median. It's one of the more important things. So the median. So let's figure out Q1, Q2, Q3, and Q4. So as you know, the number in the middle, that is your median, so that's Q2. Now, the highest value will be Q4. Okay. Your lowest value will be Q0. Not even really. Like Q0 is like over here, This is not really Q0. So let's go ahead and figure out what Q2 is. Okay, so from the middle, that's the 1, and there's 2, and it's like calculating the median between the 50th percentile and the last number, and of course this is your Q3. Now there's a way to do this in Excel, and I'm going to pull up Excel right quick. Well, yeah. So let's go ahead and get Excel going here. So I'm going to zoom in so you can see what I'm doing. So let's go ahead and, a nice even, is odd, I think, yeah. So a nice odds. Now one of the ways we can calculate our quartiles here, equal median, you can click it, highlight the whole thing. There's our 50th percentile. Okay. Or Q2. 20th percentile. 5th. 100. And we'll just call this min, okay? So, alright, we can calculate each one of these, okay? So we can equal quartile. See this? Returns a quartile of a data set based on percent values from 0 to 1, or this function is available for compatibility with Excel 72000, returns a quartile. So we're just going to do, and then this is returns a quartile of the data set based on percentile values from 0 to 1, and it's exclusive. So, it only counts things once, so we're just going to do inclusive. Now you see here, the argument, okay, array. That means the data set. So that's your data set. After that, you hit comma. Now you'll see the second argument right here, it says quart. And then look over here. 0, first, second. So we're just going to type in 1. Okay, and we're going to close that up. And there it is. It will return 4.5 is the as the 25th quartile. Now, 20 is the first quarter, or the first quartile. Let's do the same thing again. Equal quartile. We're going to go to quartile inclusive array. See, right there. So highlight the array or data set. Now we're interested in the third quartile here. So comma 3 close. There it is. Same thing. Quartile. Highlight the entire thing. Comma 4. And there you have that. And here is our, of course, if we want to do what minimum number is, we can hit equal min. And there's our minimum. So, and that is how you kind of put out that data set, the quartors for that. Let us continue. You can go ahead and look at the steps here. If you want to calculate it like so, you can multiply n by 0.25, but I just recommend doing the Excel way I showed you. Oh, I forgot a step. You need to get the interquartile range. Okay, so interquartile range is Q3 minus Q1, as it says right here. So all we gotta do is we go equal Q3 minus Q1, and there is our interquartile range. Alright, now let's move on to that mean deviation. Okay, so I'm going to make a new data set. We'll go, and we're going to zoom in again. So we're going to go 5, 8, 12, 15, 14, 12, 19. And then we're going to make a pattern for Excel to pick up on, okay? I wonder if Excel can pick up on this pattern. I like to test Excel to see if it picks up on patterns. It tried. Okay, it didn't do it, but it tried. But this is enough, okay? So, we have a data set. And what we're going to do here is we're going to calculate what the mean deviation is. So, mean deviation. That's what we're doing right now, is mean deviation. And first, we want to find the mean in the data set. So let's go ahead and equal average. Okay, equal average. Highlight the entire data set. 93. So our average is 95.56. Now, that's the first step. This is step 1. Step 1 equal find the mean. Okay, step 2 equal, you need to subtract the mean from the case value. Okay, this determines what you call a deviation score. Alright, that's the deviation score. So again, we're going to subtract the mean from the case value. What this means is we're taking this number right here. We're going to go, let's go ahead and I'm going to make a new row here first before we do anything. Insert. And we're going to, this will be mean. Okay. This will be the mean deviation. And this will be our data. Okay, this is data. And so let's go ahead and subtract the mean from the case's value. Okay, so equal case value minus the mean. And you can see here it's going to go negative. That's not a big deal. That's to be expected. Okay. Now I'm going to show you a trick. Notice if I click and drag this down once, it just gives me a duplicate of this number. Okay, that's because when you drag Excel, you tell this green box. Oh, there's a green box here. You can't see it very well, and I can't zoom in on it. But there's a green box on the bottom right-hand corner of the screen. You can see my cursor becomes a black plus when it goes over instead of the white plus. You can click and drag that down, and it clones, but the calculation you had, but one row down, and it moves everything equally. Now you can control how it moves things, right, by going into this one. And let's say what we want to do here is we want to have A2 move, the blue box. We want the blue box to move. See how it's color-coded blue and red. But we want red to remain locked into place. What we do to do that is we enter a $ in front of the C and a $ in front of the 2. Now that means hold constant or hold steady. So we can click and look at this. What happens? It actually calculates the mean deviation for this number right here. And you can see now the blue box moved, but the red box did not. And because of that, we can now do this many math problems in only a matter of time. And this is the mean deviations for all of those. Next, step 3 equals find the absolute value of each deviation score. Okay, so all the absolute value is, the best way to think about it is, we'll say absolute value. Okay, let me say ABS. All the absolute value is equal ABS. That does the absolute value of it. Just do this and just click once, hit OK. Drag. Now the absolute value, what that does is it's the distance from 0 this number is. So it's always a positive number. Absolute value is always a positive number. And if it's a negative number, you just remove the negative, and there is an absolute value. And if it's a positive number, well, it's the same number. So just click and drag down. And here is the absolute value of our mean deviations. Okay. Step 4. Okay. We sum the absolute values. So let's go over here. Step 4. Sum the absolute values. So I'm just going to go over here and say sum of ABS. And we're just going to do a sum calculation equal sum. I'm just going to highlight everything. Hit enter. And there is our sum of absolute values, right? And then finally, step 5, the final step, this is calculating mean deviation. You divide by sample size. So to quickly find sample size, we're just going to go, I'm going to say sample size right here, okay? Sample size equal count. Click it. Highlight the entire data set. Hit enter. And here's we have a sample size of 93 for this data set. All right. So now we have to divide the absolute value by the sample. I'm going to say mean deviation, because that's the whole goal for this, is to get the mean deviation going. Equal sum of absolute values divided by sample size, and we have our mean deviation right here. That's how you calculate the mean deviation. Since this is recorded, you can go watch that again if you need to. Let's move forward. This is how to do it on the PowerPoint if you need to do it on the PowerPoint. Standard deviation and variance. So for this, I am not going to make you calculate standard deviation on your own self. All I want you to do, this is how you do it though, by the way, if you ever need to do it, you got to find the mean. For each case, subtract. This sounds familiar, right? For each case, subtract the mean from the case's score to determine the case's deviation score. Okay. Now, instead of absolute valuing the score, we square each of those deviations. So instead of doing the absolute value here, we would instead, square those deviations. So equal the square root. Well, I'll just do a manual calculation of square root. So we can go equal this, not that. Equal this times this. So it's the same. You multiply the same thing and you get the square root. Again, we can just click and drag it all the way down, like so. We don't have to lock it anything because we're all we're doing is dragging the same box down, so no locking is required from that. And then you divide the sum of the squared deviation scores by sample minus 1. So that's what, and we'll go see this n minus 1 over here. Oops. See this? Oops. Where am I at? See this n minus 1? That is just sample minus 1. That's how you get variance. And then you calculate the square root of that. So now all I want you to do is to simply hit this equal STD P. Now recall the sample versus population. STD sample, it's based on sample, right? But we're working with the entire population of this data set, so we're going to hit population, standard deviation population, highlight the entire data set, hit enter, and what do you know? Here's our standard deviation. Okay, that's all I need you to do. I don't need you to manually calculate standard deviation ever. So this is standard deviation. So don't worry about the long calculations of that. Worry about the long calculations of mean deviation though, because that's going to be on your test. IQV is a great way to calculate dispersion and how variance at categorical levels. Recall that categorical variables are things like eye color, race, gender, so on. You can't put rank values on these numbers. So I'm going to go ahead and I will show you an IQV calculation real quick, and I gotta find it again for those that watched me do the lecture on Tuesday. So let me go into my Blackboard real quick. Find it. It's here somewhere, I'd imagine. Here it is. I'll go ahead and upload this. So this is what you call an IQV calculator, and you don't have to worry about making it yourself, but I got it pulled up right now. Okay. So IQV, what this does is it is the ratio of the amount of variation observed in a distribution of scores to the maximum amount of distribution that could exist in a score. It's just going to shoot out a IQV is a a percentage value of how heterogeneous or homogeneous your data set is, or in other words, like how much diversity is in your data set. Like if you're looking at race, right? You will look at race diversity in the United States. You can run IQV on that, and you can get the exact percentage of racial diversity in the United States with this stat. So again, racial diversity, as I said, is a good one to use. So if the population only included whites, the IQV score would be 0. Now 0 means no diversity. 1 means full diversity. In other words, everything's equal, and there's across all categories that you have. And I'll show you that in time. Here is the formula for IQV. You see the K is the number of categories you have. Let's say that you have 3 races that you're looking at, or we'll say 4 races. We'll say white, black, Asian, and other. All right, so that would be your 4 categories. So K would be 4. The number of cases, which is N right here, your N, and then you square the sum of squared frequencies. Remember that sigma is sum. It just means sum. It's a shorthand way to write sum or add everything together. Sum of squared frequencies, okay? And then K minus 1, and this is your categories minus 1, which is it's a calculation of variance. I'll show you this on. You don't have to ever do that. I don't expect you to do that, but what I do expect you to do is to use this sheet that I'm going to provide you with. And if you look down here, right here is the formula that you just saw on that PowerPoint. I can't zoom in on the top bar there, but that's the formula. And So all you gotta do here, let's say, all right, we'll do race, we'll do white, exactly what I just said, okay? Just type in the races here, okay? Asian, we'll go other. All right. Now let's say in our data set we have 10 white folks, 7 black folks, 3 Asians, and 2 others. All right. Now if you come down here, oh, look at that, IQV calculated as in 88.7% diversity is in this data set. In other words, as you can see here, there actually is quite a bit of diversity going on. Now let's say that I do 10 white folks, 0 black, 0 Asian, 0 others. Now it went to 0% diversity. Okay. Now let's say holding all. Let's say that I want to. I want to say everything's equal across all categories. 100% diversity. You see how this works? So, again, let's say that we want to do that. That's high diversity. Now we say we only have one of each besides white. You start to see, it drops off pretty bad. Yeah. So that is IQV. Just report that as it says from the data set. Not the sheet that I'm going to share. I'll upload it later. So let's say racial as follows. This is an example of just what I just showed you. So, and then finally, percent change. Okay. So for percent change, I'm actually going to bring up the Google sheet that I assigned you for homework. And I'm going to show you how to do percent change on that. Alright. So here we have Google Sheets. Now for Google Sheets, okay? Google Sheets, I can make another sheet here. Alright. So Google Sheets is about the same thing as Excel, honestly. And, it does the same thing. We'll say we have data. And you can do the same, bells and whistles with Google Sheets as you can with Excel, except it's live and you can share it. It does do suggested autofills, equal median, equal mode, all this nice stuff, is on Google Sheets. Standard deviation, stdev, you can just do stdev. You can get the standard deviation. Sometimes, you have to work in Google Sheets maybe as a product of the place you get hired at, right? Because a lot of places that hire, especially like in business practices or any kind of like money management place, or even like when you're entering data, Google Sheets is a great way to do it because of what it's free, and it's actually a very powerful tool. So businesses and places that you might work might be using Google Sheets to record keep. So you can actually do percent change in Google Sheets based on, and like I said here, your instructions are in your homework. But let's say that we're going to do percent change, okay? So let's refer back to the PowerPoint. Percent change measures the difference in values using percentages. This is a great way for simple evaluation of program impact or magnitude of change. So your formula is your after value minus your before value. So let's go here. Okay, so we're going to do after value. So our after value is 2015 because it's more in the future. Okay, minus, hit minus your before value. Okay, that's the first part of the calculation. That is the first part of the calculation. And then what you want to do is you want to divide by the before value. Equal, okay, this number, which is the calculation you just made, okay, minus before. And not minus, but divided by before. Okay, and that gives you that. Finally, we want to multiply by 100. Now, there's two ways to do this, right? You can do this. You can take this number, and you can multiply that by 100. And don't opt to hit the percent, because if you hit percent, it goes a little crazy. See, look, bam, it goes like nuts, okay? Because you're converting into percentages twice. That times 100 already converts into percentages for you. So let's go ahead and remove those percentages. And instead, we can just say, hey, Google Sheets, convert to percent. So this is the same as this. It's just ones in percent form. There's a decimal form. Now, let's say that you're good at Google Sheets and you want to really test, like, some of the things you're doing. All right, so we're just going to do the whole math problem in one go. Okay. So after value minus before value, after value minus before value, close parentheses, okay, divide by before value, and then we want to multiply by 100. And as you can see, that we get the same answer that we got up here as we did down here. Again, there's a formula for it, just as it's written on the PowerPoint slide. What do you know? You can click and you can drag it down. We got what? 5 states. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and it gives us our answers. Okay, that's all there is to it. And once again, if you don't want if you want to hit the convert to percent button, you can just remove the times 100 from it, and then hit percent, and it gives you percentages. So that is how you do that. Okay, I'm going to clear this out and delete this too, because this is a live sheet, and that is percent change. Here's a quick way to go for Google Sheets, some quick references for what you need to do, which moves us into our next PowerPoint. If I can find the darn thing. Here we go. Your types of variables. So, what is a variable? Well, variables, it's anything. Literally, it's anything, okay? So, it can be age, gender, race, weight, height, number of cars owned. It's literally anything. It's the ingredients in your project. And whatever you... So, when I refer to the word variable from here on out, what I'm going to do is I'm going to it's just what we're working with. It's the plugins to our formula, okay? That's the variable. It can go up, it can go down, it can stay the same. As in, like, weight, you can increase, you can get heavier. Your weight can decrease, you can get lighter, or your weight can stay the same over time. And your weight in that case would be a variable because it changes, or maybe it can stay the same. It can change, okay? So that is what a variable is. There's two major types of descriptive statistics. And when a researcher needs to describe the distribution of a single variable, it's called univariate descriptives. Now, univariate, uni means one, like unicycle. And when a researcher wishes to describe the relationship between two or more variables, it's called bivariate. Again, bicycle, two variables. And then you have multivariate, which is 3 or more. Univariate descriptives are things such as percentages, averages, and graphs, and it can all be used to describe univariate stats. So, for example, summarizing the income distribution of a community, you can do this with graphs, like a pie chart, for example, and data visualization. I'm going to add a section to this course a week that we'll do data visualization in, okay? And what you call this is data reduction. So, just you're taking a large amount of data and you're compiling it down into a small amount of visuals so people can understand what you're talking about. So, bivariate and multivariate, these help us understand the relationship between two or more variables, and these are called what you call measures of association, which allow us to establish the strength and direction of a relationship. This helps us investigate the causation and prediction. And measures of association cannot by themselves prove anything. You're just adding evidence that things are related. So you're not proving anything. You're just saying, oh, hey, here's evidence that they are related. And it's more evidence to the effort of trying to prove and establish a relationship. But, you need to do it more than once over the course of, time or place or whatever. So let's get into these variables and this bivariate relationship stuff, okay? So studying the relationship between two variables. You got time studied and grades. And here's a question in this case. What is the independent variable and which is the dependent variable? Cool. So we have time studied and grades. Now, when you're talking about the independent variable, all right, you're talking about the thing. It's just we have your independent variable IV. Okay, and the IV, he likes to chill. He doesn't let his bad peers influence him. Okay, so when the bad variable, humor me here, okay, comes up to the independent variable and he offers the independent variable some drugs, well, he's not influenced at all and he has nothing to want to do with it. Okay, so this is your independent variable, standalone. It doesn't impact. It doesn't. It's not impacted by anything. It's not impacted by peer pressure, for example. Okay, it does what it wants to do, no matter what. Now you have the dependent variable on the other hand, and then you have the bad variable approach the dependent variable and offer him some drugs, and he's like, "Yeah, man, here's the money," and he gets influenced by the drug. All right. So, with that, me trying this analogy for the first time, tell me how it worked. Um, you can look at it down here and say, okay, you have the relationship of studying the relationship between two variables, time and grades. Okay, does time spent studying always impact grades in a positive manner? Now, what I'm going to do here is you have a relationship. You're saying my grades and time studied. All right. Most people would argue that how much time you spend studying influences this, okay, your grades. Therefore, your dependent variable, the one that's being influenced here, that's your grades. And this, your independent variable, is time studied. Okay? So time studied is your IV, and your grades is your DV, or your dependent variable. Alright, so as you study more, let's say that let's not even say, let's be more specific. Let's say you study 2 hours, okay? And then you study for 15 minutes on the next test. When you study for 2 hours, you notice that you had increased grades, and when you studied for 15 minutes, you notice you had decreased grades. In other words, time studied is influencing this grade. The more time you put into it, the better you do, and the less time you put into it, the worse you do. And what this causes is this is called a positive relationship. Okay, meaning as one goes up, the other will always go up, and vice versa. Okay, or if one goes down, the other will also follow it and go down with it. So the independent variable in this case is leading the way for the dependent variable. The independent variable increases, the dependent variable will increase. Okay, the independent variable goes down, the dependent variable also go down. Now, if you get into a relationship that is what you call a negative relationship, the independent variable still influences the dependent variable, but the dependent variable in this case runs away from the independent variable. In other words, if the independent variable increases, the dependent variable will go the other direction and decrease. Okay? In the same way, if the independent variable goes down, the dependent variable is going to run away from the independent variable because, again, that's the influence. The dependent variable sees the independent variable and wants to stay the hell away. And so it runs away. So that's how the independent variable influences the dependent variable. Inferential helps us generalize a population. So voters in the United States, unemployed whites in Appalachia, sophomore football players in the Midwest, so on. So inferential statistics then involve using information from a sample. Remember, sample versus population. Population is the whole pizza pie, and a sample is when you take a slice of that pizza pie. Okay, so population is your entire data set, and sample is a portion of that data set. So from quick definitions here, all right, so you have a hypothesis, which is a stated form of a relationship, okay, between two variables. the relationship between your independent variable and your dependent variable. Your independent variable produces an effect or impact on the dependent variable. Okay, again, it's just like we were just talking about over here. In this case, the hypothesis was if I study more, then my grades will increase. Okay, that's the hypothesis. Or I hypothesize that as I study more, my grades will increase. Okay, so these are what, and I kind of covered directional hypothesis already. So when you specify a positive or negative relationship in your hypothesis, it's called you have to do a null hypothesis. Okay, so now we have the actual hypothesis or your alt. This is called alt, so your actual hypothesis. Okay, and this is called alt. It's also called H1. Okay, it can be either. In your alt hypothesis, going back to the time studied thing, is as I study more, my grades will increase. That is the alt or H1. Grades go up. Okay. So, and then we'll have HO. Okay, H0. Or this is what you call null hypothesis. And what you're saying for null hypothesis is no matter how much I study, my grades don't move. Okay, that is null. In other words, the independent variable has absolutely no impact on the dependent variable. Okay, so null hypothesis means no difference. That's what it really means. And for every hypothesis you write, you have to make a null hypothesis. And all the null ever is, and it's always the right answer, is no impact. Variable x, or my independent variable, does not influence my dependent variable. Okay? Does not influence. And so the variables I am testing produce no difference. And we want to reject null hypothesis. We always want to reject this guy right here for our hypothesis, because if we reject null, that means there is good evidence saying that our alt is correct. Basically, when we test something, we want to see the test have some sort of impact instead of nothing. Nothing is not what we want to see. Going back to research design, it assigns subjects to the experimental and control groups. There's random selection involved in this process, and the key point of classic design. And random selection means that every member of the target population has an equal chance of being selected. Okay? So let's say that we have 5 marbles in a bowl. So we're going to make a bowl. Okay, and we're going to put 5 marbles in it. 1, 2, 3, 4, 5. Every time we draw from this, we're taking a sample, a random sample, because we're doing it blindfolded. Okay? We're not looking. And each one of these marbles has an equal chance of being pulled. They each have a 1 in 5 chance, no matter what. Now, as we draw it, we put it back, because if we put it back, it stays a 1 in 5 chance. But if we don't replace the marble, then the next marble has a 1 in 4 chance of being drawn. So it has a different odds of being drawn at this point. And one's a 20% chance of being drawn because all 5 marbles are present, and this is a 25% chance of being drawn because there's only 4 marbles in the jar. Here's your experimental group. X represents intervention. And one of the things that we can talk about with experimental groups is medicine. Right? Let's say cold duration. You can say we're going to do a study on cold duration, and we're going to pull 100 people. Okay, our N is 100, so 100 people. And we're going to divide them into 50. We're going to divide them into 2 groups of 50. Okay, one group. Okay, one group. So this is group 1. We'll say group 1. Okay, we will give them the cold medicine. So 50 people got the cold medicine. So 50 people got the cold medicine. Now group 2. This is 2. See, there's no X here. There's an X here. That means medicine given. Okay. There's nothing here, though, okay? Meaning that 50 people did not receive the meds, okay? And that's it. And these 50 people are randomly selected from the population of 100. And we throw them into different groups. And then at the end of the project, let's say they all had a cold, and they all recently got their cold. They got their cold that very day. Okay, so on day one, they all had colds, and let's say that we measure data for a month. So we have 30 days of data, and we can look, and we'll say on day one, was everyone still sick? Yes. So we can mark them all yes. Okay, day two, was everyone sick? Yes. And we keep going until we get about day 7, right? And then we start seeing people in the experimental group right here get better. And then by day 10, all of the experimental group is better. Whereas like on the control group, which didn't actually receive a pill, they just got a sugar pill, you see like on day 15 they start to get better. And I'm exaggerating just to kind of make a point here. But this is how you do the classical experimental design, and you get to see the difference in the medicines administered. Quasi-experimental is the same thing as experimental. We have to do quasi-experimental in social science. It's almost the same thing, I should say. It occurs when random selection is impossible, and we have to assign groups based on some needs or wants because people are different. Some have different needs, some have different wants. Sometimes you just can't randomly select at all, and that's just social science, and that's called quasi-experimental when random selection is just not possible. Okay, but you still do the experimental control group design. So there can be ethics involving research. This is called the Milgram experiment. I encourage you to watch this YouTube video. I went over it in my in-person class because the sound wouldn't play, but the online course you have the good fortune to be able to play the video. So watch that, and you'll see what the unethical part of the Milgram experiment is. The reason why this experiment was unethical is the people participating in the experiment did not know that the other person on the other side of the wall was an actor. Okay, so they had a lot of psychological distress involving it, and that hurt them. That mentally hurt the people taking it. So that was an ethical experiment. So let's talk about discrete variables. Discrete variables are things that you can't divide into two. You cannot divide a child into two halves. All right, I can't take my stepson and say, okay, I'm going to cut you in half and create a half of a stepson. He'll die. You can't do that. So instead, he is just one person. Okay, you can't divide one person. Not unless you're killing them. So that being said, you cannot subdivide a discrete variable. So people per household, siblings, children, or cars owned. Now what you can't. Now sometimes you will get a legitimate decimal, right? Let's say that we have the stat 5.2 children. Okay. Now, recall that I said you can't have anything besides a whole child. Well, in the case of, let's say that you survey 500 households, okay, and they all report their kids. Let's say, this is going to be a high average because I said 5.2. Let's say everyone reported that they had between 4 and 8 children, okay? But the average came up to be 5.2, meaning the average household has 5 children that is about 20% of the way until it's 6. I guess you could say it that way. But so the average household has 5 children, but sometimes the average household has 6. Okay, that's probably the best way to interpret that. But it's close. It's always closer to 5 in that average. Continuous variables is time. If a score has it can be divided infinitely. Variable is continuous if it can be divided infinitely, so time and distance. In other words, you can keep breaking down that 10 seconds, 10.5 seconds, 10.56 seconds, 10.563 seconds. And it does actually keep going and going and going. You can keep breaking it down, and you will die of old age before you finish it because that is the concept of infinity. It keeps going. Okay? So, continuous variables. That is what it means by continuous variables. So, time, distance, you can keep breaking that distance down to more specific distances. You have 1 mile, right? But it's never exactly 1 mile. Like 1 mile from here, there's probably an exact 1 mile, but you can get down into it. Like, from here to Lexington is probably like some odd miles and some amount of decimals that those decimals keep breaking down into. That would be a continuous variable. Levels of measurement, you have 4 levels of measurement I want to talk about. You got normal, nominal, ordinal, and interval ratio. Your nominal is, of course, things, we already discussed with IQV, things that you cannot rank, okay? So you can't rank genders because one's not better than the other. You cannot rank zip codes because while they are numbers, for example, this is the zip code that I live in, 40214. 40213 is not lesser than 40214 because these numbers hold no value. All right, they're just identifier numbers. So just because it's a number does not mean that you can rank them. Race, there's no one race that's better than the other. Religious affiliation, there's no one religion better than the other. Place of birth, no matter where you're born, you're still a person. All right. So these are called nominal level variables, or categories rather. So they must be exhaustive and cover all the types of observations made. So in other words, if you hand out a survey, you want to put down your race. Well, you want to put down uh, we'll do race. It's easier. All right. So we can say white, black, and I'm running out of room here, so I'm just going to keep it down to these two, and I'm going to say other. Now this other option covers this must be exhaustive because everyone can still answer into other. All right. The categories must be mutually exclusive, and collectively mutually exclusive means everything is different. You can't say, oh, you know, you can't list white twice. Okay. So no real ordering in the list of categories. Ordinal variables must have a rank ordering, but are not necessarily, but can be. So examples include social class. So working, middle, and upper. When we do working class or middle class and upper class, we could get a general idea of like 0 to I don't know, $30,000, and then middle class we can say 30,000.001 because we have to be to like and these aren't the real numbers. I'm just giving you examples. 55K, and then upper class of course can be 55K plus if you want to do that. Now upper class really is not 55K plus. It's more middle class numbers, but I wanted to keep things kind of So, and in other words, you can say, okay, this person has less money than this person, which has less money than this person, and this person has the most money. And that gives a rank order, but they are into categories. So it's rank order categories. And you can, you've seen surveys where it's like on a scale of 1 through 5, how bad does it hurt? Okay? And, with 5 being the most pain and 1 being the least amount of pain, or no pain. You can say 0 too, right? No pain. So that's how that is. That is an ordinal scale or an ordinal category. And then interval measures have equal units measured between them. Okay. IQ, continuous variables, that is a talking about that can have decimals. Temperature is another thing that we measure at interval level. So, between 1 and 2 is an equal distance. Between 3 and 4 is an equal distance, and so is 5. In other words, these are intervals, so it's a number. Okay, if it's a number that has a rank value, that has actual weight behind the number, and they are equal distances apart, it is interval. Ratio, everything is featured in the interval variable except ratio. It also features 0 point and under. This is the highest level of measurement. You can always go down while converting, but never up. So what we're going to do in this stats class, as most people do, is we have what you call interval ratio. And I'm going to refer to it as such. It is called interval ratio, and it includes both these categories. And that's it for this week's lecture. I'll see you next week. Thank you.